I think we can begin now. So our first talk is by Victor Flambon, who will discuss searching for, well, actually, I think a lot of different topics. I think Victor will best describe his work. So whenever you're ready, Victor, please.
Okay, so I try to describe 4 topics if I have enough time. First topic is thorium nuclear clock. So the aim is to search for variation of fundamental constant, like fine structure constants, strong constants, masses, search for dark matter, which causes also variation of fundamental constant. And I will not talk about this. These clocks also may be used to search for the violation of fundamental symmetries, like Lorentz invariance and Einstein-Equilibrius principle. Okay. So we try to accommodate all possible clocks, all possible transitions. So optical transitions, atomic calculation for quasar absorption spectra, for atomic clocks, dependence on fundamental constant, molecular transitions, microwave transition, Mös-Bauer transition. But so far, the nuclear clocks are the most sensitive to variation of fundamental constant, and also as a source for, as a possibility to search for dark matter. So this is the most sensitive clock, and I just tell you the news. Why clocks are so sensitive? So first of all, the interval of frequencies is in laser range, and the width is very small. Systematic effects are very small. I will not describe them, but there was an estimate of systematic effect. So it's a very good clock. Then first estimate immediately shows that these clocks are extremely sensitive to variation of fundamental constant. So a relative change of frequency may be 4 orders of magnitude even bigger. Coefficient of enhancement is maybe even bigger than 4 orders of magnitude. So this is a relation between frequency, relative change of frequency, and relative change fine structure constant, relative change of strong interaction. Just for comparison, if for current limit for delta alpha is about 10 to the minus 17, for thorium clock shift will be about 200 hertz, while for atomic clock 0.01 hertz. So 200 hertz is something which a student can measure in principle, but with 0.01 hertz is an absolute state of art. It's very hard to do it. So there were calculations of sensitivity of thorium clock to variation of fundamental constants, but the results are spread over a big interval of possible values. So we tried to do it in a different way. We tried to use experimental data. We express sensitivity to alpha in terms of difference of measured radii of a nuclei and electric quadrupole moments of a nuclei. So it's a formula which expresses actually Coulomb energy difference between the ground and excited states in terms of R squared and quadrupole moment. And this relates in sensitivity to alpha. So all what experimentalists should to do is to measure atomic frequency in ground state of the on thorium nucleus. So nucleus is in the ground state, and you measure frequency of atomic transitions and frequency when nucleus is in metastable excited state. It's long-lived, so it's more than enough time to measure atomic transition frequencies. And this actually was done in 2 publications with very high accuracy. They measured a change of radius to very high accuracy. Quadrupole moments is not so good, so we still have some uncertainty in the value of Coulomb energy difference between the ground and excited states. So there was some uncertainty in the difference of on insensitivity to variation of alpha. So recently we did the next step. We assume a model of constant nuclear density. If in this model of constant nuclear density, change of quadrupole moments between ground and excited states is related to change of nuclear radius, because you deform nucleus and quadrupole moment is linked to nuclear radius. So if you measure nuclear radius, you also can find change of electric quadrupole moment. Using this procedure, we use experimental values of change of nuclear radius and find change of Coulomb energy and sensitivity to variation of alpha. And our final result was delta omega over omega about 0.8, 10 to the 4, delta alpha over alpha. So indeed, there is a huge enhancement of variation of alpha in this transition, about 4 orders of magnitude. So just simple explanation, why enhancement is so large. Total Coulomb energy of a nucleus is 10 to the 9 electron volts in thorium. So it's 1 GeV, 10 to the 9 electron volts. Using measured delta R squared, we found difference of Coulomb energies between excited and ground states. It's only 67 keV, so it's less than 0.01% of Coulomb energy. And so it looks like a very small number, but when you divide this Coulomb energy by frequency, which is only 1 electron volt, you see that delta omega over omega is with 7 10 to the 4 electron volt divided by 8 electron volt. It will give you enhancement factor with 0.8 10 to the 4. So enhancement actually happens because omega 0 transition frequency is extremely small on a nuclear scale. Typical nuclear scale is MeV, and here we have only 8 electron volts. This is why relatively small change of Coulomb energy between ground and excited states give us very big enhancement in sensitivity to delta alpha over alpha. For strong interaction nuclei is larger, enhancement may be even bigger. So this is why nuclear clock may be so good to search for variation of fundamental constant and to search for dark matter, which causes this variation of fundamental constant. Next topic, I'm going through different new results obtained recently. It's nuclear time and parity violating moments and axion dark matter fields. They induce atomic and molecular electric dipole moments, which are measured in experiment. There are new results in this area. First of all, we know that nuclear electric dipole moment cannot be measured directly because electric field or external source of electric field can completely screened on the nucleus. So this value, shift of energy, which is electric dipole of a nucleus times nuclear electric field which penetrates the nucleus, vanishes because electric field does not penetrate the nucleus. It's screened by electrons. There is a way around this. If you consider oscillating electric field, it penetrates nucleus. So this is way we can go around shift theorem. So I derived the formula which relates electric field in the nucleus to external field, which contains frequency squared, polarizability, nuclear charge. When frequency is small, electric field does not penetrate. So because effect is proportional to omega squared, omega is 0, frequency of oscillational field is 0, there is no field in accord with the shift theorem. But frequency is not 0, we have non-zero effect. Moreover, we can have enhancement because if you come to resonance, we have Rabi oscillations. So electron in, say, valence electron moves from ground state to excited state, and its field on a nucleus changes, but field of external electron is extremely big. It's much bigger than any field that may be achieved in laboratory. It's nearly 10 to the 10 volt per centimeter. So this oscillation of electrons causes electric field in the nucleus, which is pretty big and allows us to feel nuclear electric dipole moment. Also, it may affect nuclear reactions. This situation is even more interesting in molecules because for static field, nuclei in molecules are very efficient screeners. They have big charge. So nuclei participate in screening as well as electron participate in screening. But when you apply variant field, which people oscillate, nuclei are slow. They are not so good in screening. So field on the nucleus is bigger by ratio of molecular mass to electron mass compared to atoms. So this is first factor of enhancement due to slow motion of nuclei. There is another factor of enhancement. Polarizability for small frequencies is very big. So energy denominators are very small. in these formulas for electric field in the nucleus. It give us another factor of enhancement, which is molecular mass over electron mass. And if you go to resonance, you can have even more enhancement. So molecules are very good for this problem because nuclei are slow and screening is small. Screening is not so efficient, and all energy denominators are very small here. Finally, instead of oscillating electric field, we can consider oscillating nuclear electric dipole moment. This happens if nuclear electric dipole moment is induced by axions, by axion dark matter field. This oscillating nuclear electric dipole moment also enhanced in atoms for the same reason as electric field is enhanced. So nuclei are not good screeners, and electric field, and in this case, electric dipole moment is not so efficiently screened. One more topic, how we can go around shift theorem. We can consider effect of nuclear polarization. We know that electric field is screened, but we can, instead of considering one photon exchange, we can consider two photon exchange. So there is nuclear polarization effect. Usual nuclear polarizability is electric dipole twice, or magnetic polarizability, magnetic moment twice. Yes, matrix element of magnetic moment twice give you magnetic polarizability. Electric dipole moment give you electric polarizability. But if you consider mixed case, one vertex is magnetic moment, another vertex is electric dipole moment, it will be time and parity violating polarizability. So it produces efficient time and parity violating interaction, which lives on short distances, it's not screened. And you have effect produced by time and parity violating nuclear forces inside the nucleus. So it's a way to go around shift theorem. It's a relatively recent result. And what is important, that we don't need nuclear spin anymore. So all experiments which are used to measure electron-electric dipole moment may be used to measure this TPO nuclear polarization and get limits on most important fundamental interactions violating time and parity. For example, on theta term and QCD. So this is another way to go around shift theory, nuclear polarization. Finally, it's old story, shift moment. So electric field of a nucleus, which is just density divided by distance, it's just electric field of the nucleus. Dipole component of this field is screened by electrons. This is a second term here, which is screens dipole moment field, but it's screened outside. Inside is not completely screened. There is some field which survives inside the nucleus. So you can get this field using multiple expansion, and this field inside the nucleus appeared in the third order of multiple expansion. So because it's third order, you have extra nuclear radius squared here in the formula. So the first term here in the shift moment expression is usual term coming from the first term of potential, and second term is screening term. So we actually named this moment. Shift never calculated it. We produced calculation of a shift moment. So this is old story. A new story, you can have a huge enhancement of this moment in nuclear with octopole deformation. Actually, even this story is not so new. 96. So what happens if nucleus has octopole deformation? Shift moment is proportional to octopole moment. It has a collective nature. So shift moment will be collective. Okay, but this is not enough, because when nucleus rotates, this shift moments averages out, similar to electric dipole moments. It's forbidden by time reversal invariance. However, when you have octopole deformation, you have doublets of opposite parity rotational states. So it's similar to lambda doublets in molecules, or omega doublets in molecules. So there are doublets of opposite parity states in this case. And what we can do, we can mix these states by time and parity violating interactions. We have three factors of enhancement there. First, shift moment has collective nature in the body frame. So it's big, it's a collective moment. Then small energy interval between doublet components. It's something like 0.05 MeV instead of 8 MeV. So energy denominator is small. And finally, large matrix elements, because these doublet states build from the same internal states of a nucleus. So basically, you need matrix elements of time and parity violating interaction over nucleus with octuple deformation. And this matrix element is big. It's expectation value. It's not a small non-diagonal matrix elements. When you have all these three factors of enhancement, shift moment may be enhanced up to 3 orders of magnitude. Okay. Moreover, we don't need static octupole deformation, because if you look to formula for this estimate for shift moment, it contains octupole deformation squared. So it may be dynamical deformation, like an oscillator. Nucleus oscillate, but slowly with big amplitude, with octupole mode, and beta 3 squared is not 0. So average value of beta 3 is 0, like an oscillator. Average value of x is 0, but average value of x squared is not 0 because of this oscillation. The same case here. So we need static octupole for enhancement, or just low line octupole vibration mode, vibration with a big amplitude. We found a number of nuclei which has this octupole moment, or maybe soft octupole mode, where shift moment is strongly enhanced. So there are many recent experiments and calculations which confirm existence of this octupole static or dynamical deformation. This is old story. New story. The experiments were done with radium only. There are 2 papers published by Argonne Laboratory who measured electric dipole moment of radium. But radium has only 15 days lifetime. When this, since 96, there are a lot of new information obtained. And now we know that other nuclei also may have octupole deformation, or octupole or slow octupole deformation, static or dynamic. So for example, actinium, at least 22 years, neptunium, 2 million years, europium is a stable atom. It's also probably have octupole deformation or soft octupole mode. There are even other candidates like uranium and dysprosium, thorium, which may have dynamical octupole. The extreme case is palladium, which has very close opposite parity levels, but it's still not confirmed. So we found opportunity to improve with measurements of time reversal and parity violation by measuring electric dipole moments of atoms and molecules, if you consider this nuclei with octupole deformation. Moreover, just conference finished last week, but there is big interest to measurements in molecules, because now the best limits on electric dipole moments are obtained in molecules. For example, for radium oxide, effect is 200 times bigger than thorium fluoride. It's another molecule which is used to measure electric dipole moment. For a number of other nuclei, which I mentioned, there are corresponding molecules, in fact, maybe even bigger. For example, for actinium nitride or actinium oxide, plus effect is maybe 400 times bigger than thorium fluoride. So this long-lived nuclei may be used to build molecules and measure very efficiently effects of time reversal and parity violation. Another effect which may be considered is effect of Axion-like particles. You know, Axion is a very popular candidate for dark matter. It's also solved some strong CP violation problems. So it's a very well appreciated candidate for dark matter and new particles. So we can see what kind of effects this Axion may produce in atoms and molecules. Actually, exchange by these particles produces macroscopic some forces between different electrons and nucleus, or between 2 electrons. So we can calculate this effect and compare with macroscopic limits on fifth forces. So there are a lot of possibilities. You see atomic electric dipole experiments with atoms, cesium, thallium, xenon, mercury, molecular EDM experiments which have been done, and also experiments which is currently in progress with term OH. So for all these systems, there were calculations of axion exchange, and we can extract information about strength of this axion interaction with matter. So this is a picture which was drawn by Evgeny Stadnik, comparison between atomic and molecular EDM experiments and macroscopic experiments to search for new forces. And we see that in a big area of masses of this intermediate axion-like particle, atomic and molecular experiments give you very good limits. So electric dipole moment measurements may be used to study interactions of axion. And I already mentioned this, that this time imperative violating interaction may be produced by dark matter. And dark matter also may produce time variant fundamental constants. So there are two possibilities. If this scalar dark matter has zero spin in positive parity, which is, for example, dilatons and many other candidates for dark matter, we have time variant fundamental constant, and we already obtained 10 to the 15 improvement on interactions with axions or with scalars, with dark matter scalars with matter.
Victor, you have 10 minutes to go. 10 minutes.
Yes. Yes. The advantage is because effects of dark matter field are linear in this case, but normally the effects are quadratic or higher power in interaction constant. Interaction constant is very small, we have huge enhancement. For negative parity state like axions, we have time variant spin dependent effects, for example, oscillating electric dipole moments. We also have here a big improvement because effects of this field are linear. Why we do have improvement here? Because axion field produces interaction between nucleons and pions, which are similar to time and parity violating interactions, which creates shift moment or magnetic quadrupole moment. So if people measure these oscillating electric dipole moments produced by axion field, you will get information about dark matter in this case. And this again picture produced by Evgeny Statnik, comparison of recent measurements. There was measurements NEDM collaboration, who measured neutron EDM and mercury EDM, and there is hafnium fluoride pluses, Eric Carnell group, who measured EDM of these molecules. So you see this new way to search for dark matter is very efficient to produce wonderful results in the area of small axion mass. Because effects are linear, much better than results from other sources like supernova energy loss bounds. Finally, on this topic, there may be effects produced by oscillating nuclear moments, just transition between atomic and molecular states. So if you have oscillating field, it produces transition. If frequency of oscillation is equal to transition frequency, you have resonance effect. So effects may be different moments may produce effect. Electric dipole, magnetic quadrupole, shift moment. But our favorite is magnetic quadrupole, M2 transition, because photons are very strongly suppressed for M2, but axion is not suppressed. So it gives you smaller systematic effects. So these oscillating nuclear moments produced by dark matter may produce atomic and molecular transition and may be used to search for dark matter. So summary of this part: shift moment is enhanced up to 1,000 times in nuclear octopole deformation, and we identify a number of radioactive molecules where this effect may be measured. Magnetic quadrupole moment has collective nature nuclear quadrupole deformation, so there are experiments searching for magnetic quadrupole moment, which is also time and parity violating. Yes, and finally, time and parity violation nuclear polarization gives atomic and molecular electric dipole moments, which may be measured in molecules used to search for electron EDM, like thorium oxide, hafnium fluoride. So just compare all these different experiments. For first shift moment measurements in nuclear, you need to have nuclear spin bigger or equal to 1/2, because it's shift moment is a vector. For magnetic quadrupole, you need nuclear spin bigger than or equal to 1. But for time and parity violating effects, nuclear spin may be 0. So it's a simplest case. It's not necessarily 0, but it may be 0. So shift theorem is violated by oscillating electric field. So there is resonant enhancement in molecules. Axion exchange produces static electric dipole moment. As you can get limits from EDM experiments in atoms and molecules. Axion dark matter field produces oscillating electric dipole moments. It's again maybe measured in the same experiments, but we need to measure oscillating EDM. Also, axion dark matter field produces magnetic quadrupole transition in molecules induced by oscillating nuclear magnetic quadrupole. So E1 transition may be produced by oscillating nuclear EDM and shift moment, so it's not the best case. Okay, and finally, a new topic is atomic ionization by scalar dark matter and solar scalars. This is topic for different kind of experiments. It's aimed for dark matter search in underground laboratories. Of course, it's old topic, search for dark matter in underground laboratories. But what we found that relativistic Hartree-Fock calculations corrected several orders of magnitude error, because people use traditional for particle physics Born approximation. But this Born approximation does not work due to violation of orthogonality condition between bound and continuum electron wave functions. So we did these calculations more accurately with proper relativistic Hartree-Fock wave functions, obtained new limit on electron scalar coupling from recent Xenon 1T data. It's group Xenon, using Xenon to search for dark matter. Because these people claim that probably they see effects of dark matter in Xenon laboratory. So we extracted limits, obtained values, because it's a measured non-zero effect, obtained values of electron scalar coupling from this experiment, and produced data files for scalars and axions for all available detectors of dark matter. So my time is finishing, so I just repeat what we are measuring here. So we are measuring absorption of scalar and emission of electron. So it's similar to photoelectric effect, but here is scalar. Then we obtain this huge difference between old incorrect calculation using Born approximation and current and our calculation. So a mistake was that they ignored orthogonality condition between those functions, because continuum wave function, which you use plane wave, it's not orthogonal to bound electron. So produce a lot of graphs here for different detectors, and extracted limit on interaction constant of scalar dark matter with ordinary matter from both, from if it is scalar from dark matter or it's a scalar from the sun. Okay, this is graph showing comparison with other limits, and probably that's it. There isn't one more topic which I don't have to discuss. So conclusion for this part: relativistic Hartree-Fock calculations correct several mistakes for dark matter scalars and solar scalars. So we did calculation for both dark matter scalars and scalars which may be produced in the sun. And the error is due to non-orthogonality between plane wave and discrete wave functions, and error up to 8 orders of magnitude. Such effect also exists for axion, but error is significantly smaller, because for scalar it appears in a leading multiple, in axions on the first multiples next to leading. It's still important effect, but it's not so important. And we obtained values of electron scalar coupling from Xenon data. Thank you.
Thank you very much, Victor, for the very nice talk. Do we have questions? So if you have questions, you can either use the chat function down the bottom, or there's also a raise hand feature under the reactions tab.
If there are no questions, I describe my last topic here. We also found that relativistic effects increase ionization by beam scattering electrons by up to 3 orders of magnitude. It's a different effect. that scalars and axions are absorbed and electron is emitted. If heavy particle is scattered on atom, these heavy particles, of course, survives, but electrons still may be emitted. So in this kind of effects, we also found a very significant error in all calculations. We found that relativistic effects increase ionization by weakly interacting massive particles up to 3 orders of magnitude. And currently, our results are already used by Xenon collaboration for interpretation of their data. Hopefully, it will be used by all collaborations, numerous underground groups. That's it. Thank you.
So there's still time for a quick question if anyone would like to ask a question. Sebastian, please.
Yeah, hi. I would like to ask you if you have considered also fermionic dark matter. I mean, there are some models by Ruffini and collaborators that think that fermionic dark matter could be, for example, in the center of the galaxy and that sort of thing.
Could you please explain what do you mean? Because of course, if it's WIMP scattering, maybe fermionic or bosonic, it practically does not matter.
So you have considered both of them.
But for absorption, we have not considered fermionic dark matter. No. If I would be very happy to find out more about the topic of this topic, the fermionic dark matter, because usually it's not a favorite candidate and I know very little about it. Can you contact me directly and or send me some reference? I would be very happy to know about this.
Okay, yeah, sure. Thanks.
Thank you very much. Please send me the reference.
Thank you very much to Victor again. So our next talk is by Mike Tobler from Western Australia. Mike, if you'd like to share your slides, please.
Share my screen. Can you share? You can see my
I can
slide.
see your screen and it's full screen now. Perfect.
Okay,
Whenever you're ready, Mike.
Okay. So today I'm talking about some of our work on testing fundamental physics and searching for dark matter using precision resonator and oscillators and measurements in general. And this is work under 2 centers of excellence in Australia, Engineered Quantum Systems and Dark Matter Particle Physics. Here's a photo of our team, which we're growing, and we call ourselves Quantum Technologies and Dark Matter Research Lab. So I start off with this: physics is an experimental science, and one accurate measurement is worth 1,000 expert opinions, is a quote from Grace Hopper, which I like to show these days. And we are trying to look for this one accurate measurement to find new physics. Grace Hopper was a computer scientist that invented COBOL, so that's interesting how she had that opinion. So we're looking at dark matter, and as we all know, we have models of dark matter that interact with standard model particles, and then we try and convert these dark matter to standard model particles and then use precision measurements to search for dark matter. That is the topic of this session on precision measurements. And so there's a few questions when we're testing fundamental physics. We want to know if relativity breaks down, i.e., is there a theory of quantum gravity? Because these are two theories that don't seem compatible at first order. General relativity rests on the Einstein equivalence principle with 3 parts to it: university of free fall, local Lorentz invariance, and local position invariance. Also you have the standard model, which is also based on Lorentz invariance and CPT symmetry. And these two theories, we need something to link. So the approach is to test relativity with precision measurement. This can be one approach. And when we do these experiments, we rely on the theorists like Victor, who just gave a great talk on bearing fundamental constants. But maybe something like the standard model extension 2 by Alan Kostolewski, who extended the Lagrangian of the standard model to conclude all these possible Lorentz violation background fields. And therefore, the physics of our experiments will depend on these background fields, and they might depend on different sectors: photon sector, matter sector, gravity sector, for example. And we can derive different experiments to look for these different sort of effects. So another question is does gravity modify quantum mechanics? And it's the same sort of, just from a gravitational point of view of modifying quantum mechanics, could also lead to some evidence of quantum gravity. For these type of experiments, you might use a mechanical oscillator, and when you get down to very precise measurements, when your macroscopic object becomes quantum mechanical, is there a commutator relation that is modified, which could also lead. So that's two angles to look for any evidence of quantum gravity. So quantum mechanics is it possible with macroscopic masses? Does the mass modify the position of momentum commutator relations? So quantum gravity theories predict a nonlinear correction between the canonical commutation between momentum and position. And this can be tested with precision optomechanics. So in this talk, this is what we're looking at an overview of our lab, if I've got time to get through all this. First, some experimental techniques, and then experiments on dark matter, Lorentz invariance, quantum gravity, and actually a search for high frequency gravity waves. So frequency metrology, we like to show this sort of what we call a clock zoo, because it can depend on different principles like photons, different sectors. The photon sector, we can have dielectric cavities, metallic cavities, or LC circuits. At low frequency, then phonons, you can have surface acoustic waves, Bohr, and structures. And we particularly look at Bohrs and structures and dielectric cavities and high Q systems in general. Then you can look at spins, you can look at ensembles of spins, which are, can be used also like NV and diamond, spin torque systems, or magnons. We've done quite a bit of work in magnons, and of course clocks and atoms, which is Victor was talking about, and you can get very precise measurements in. We tend to focus on this area. So now we can talk about the type of experiments we do with this technology. And one of the main experiments that we're doing is searching for putative wave-like dark matter. This used to be, we call this WISPs, and WIMP and WISP-like dark matter. The community is sort of calling it wave-like dark matter now. So in this generic experiment, you have a low mass in this region, dark matter particle will interact with your physics package, and the generic experiment, you have to design this physics package to be sensitive to the dark matter of interest, could be Axion, dilaton, or something like that. And you have to have a theory of it interacting with the experiment. Without a theory of it interacting, you have nothing. So these are models and theories, and which you're testing. Then you have to reduce the noise, and eventually you'll get to the quantum noise, and this comes a quantum problem. When you come to surpass the quantum limit, you can use quantum metrology to increase the sensitivity of the experiment. The experiment can have different properties. It could be broadband, it can be resonant, it can use cavity circuits, oscillators, NMR, etc. So what we are doing at UWA, we're a member of ADMX now, and a few of our group members are spending time helping with data analysis and modeling of cavities and for the next generation and the current experiments that are undergoing. And we also run this experiment, which is an Axion haloscope called Organ, and that's at much higher frequencies. But the experience we're picking up at ADMX is invaluable for this experiment. This has just started to run. This is now taking data. We're now taking data looking for Axion masses at around 15 gigahertz. It's our first run, and we're going to keep scanning for quite a while to do a first test up at these scan up at these high frequencies. You can also look through coupling with spins. We've built some of those experiments. We're also looking at low frequency with LC type circuits, and also AC haloscopes, where you don't use a DC field, which has some benefits, some drawbacks, and some benefits. And then light scalar dark matter, which would be clock comparisons, which Victor mentioned in the last talk. Here's some recent work that we've published. One is on the organ haloscope, where we're coming up with new ways to make dielectric cavities to enhance axion experiments. And then another one with AC haloscope and a scalar dark matter, and I'll mention some of these experiments. Searching for scalar dark matter from oscillating fundamental constants seems to be a theme of this of these talks. This is from some talks at a recent conference. There was one by Victor and one by Stefan Ulmer. He showed some dependencies of different physical systems, and we were looking at this mechanical mode frequency dependent on fundamental constants to try and do a three-way clock comparison. So acoustic systems are phonons, and one can compare photons with phonons. A lump circuit is a mass spring or a LC system. A distributed one, like a drum, is like a transmission line. And where you get the highest Qs in acoustic systems are when you have the equivalent of a phonon equivalent of a Febvre-Perot cavity, is like these quartz-Bohr resonators, which are everywhere in frequency control systems for the low noise quartz oscillators. They're made from Bohr cavities. They're made where they're suspended at the edges, and the acoustic vibration occurs right in the middle and is focused just like optics in a Febvre-Perot cavity. And we cooled these down to low temperatures and got some exciting results in the range from 1 megahertz to 1 gigahertz. You get very high Qs. You can get up to 10 to the 10. And there's a piezoelectric coupling, so they're easier to read out with these, with just capacitive readout. We'll pick up a signal. These oscillators from a company called Oscillocauts. It doesn't sell them anymore. We got the last two that they sold. And we use these for some fundamental tests. We measured the phase noise in these, and they're extremely low. We got what was specified, and extremely low phase noise on these 5 megahertz oscillators, where you're down to minus 160 dBc per hertz at 100 hertz. So we also do building low noise oscillators from Sapphire, and from the photon systems. We've developed ways of getting at the thermal noise limit, and cryogenic, we're now developing a cryogenic version, which we believe will have a phase noise below minus 180 dBc per hertz when it's finished. And we're using the principle of filtering from the cavity. And this is, we have been developing this for a while, and there's a lot of know-how, which is we haven't got yet to publishing this technique yet. But lower noise oscillators are around the corner, and these will be used in our fundamental physics tests. So searching for scalar dark matter, we used one of these cryogenic Sapphire oscillators with the quartz oscillator and with a hydrogen maser. And with those three oscillators, we could measure some of the, put limits on some of these oscillating fundamental constants for dark matter experiments. And as I said, the Bohr oscillator, room temperature is on the order of 10 to the minus 13 frequency stability with a 10 to the 6 Q. But these devices have Qs of 10 to the 10 at low temperatures. And if you could use that Q at low temperature, you could get 10 to the minus 16 stability like you get in a cryogenic Sapphire oscillator. And if we could do that, we could improve the limits that we set in this paper by orders of magnitude. The experiment that we did was comparing the quartz through some frequency synthesized chain with the CSO and the hydrogen maser, and our quartz oscillator was limiting the measurements that we had. With the one that I just showed you, we could even get better. This was a different one to the Oscillocauts. we could get better. But if we could get the use of the quartz, the 10 to the 10 Q, we could get way down here and improve these experiments. So these were the results of putting limits on these scalar dark matter parameters from the measurements. The measurements weren't for that long, was on the order of a week or so. But if we could improve, the best way to improve this is improve the sensitivity. And we, in theory, could get down to here if we could work out the technical details. So can we make a cryogenic quartz Bohr oscillator using the Q of 10 to the 10? You can see here, as we measure the Q of the quartz, as we go down in temperature, that you do get to a 10 to the minus 10 loss tangent, extremely good low loss. We actually built a system where we tried to build a cryogenic quartz oscillator with Eugene, and the frequency stability measurements, there was a problem that we have to address, and we will try and address this, and maybe in the future we can see some improvement. The problem is that as you go to low temperatures, the non-linearity of the quartz becomes larger, and you get this duffing non-linearity at very low powers. Thus, when you oscillate this at any high power, you get an extra conversion, and the Allen deviation is actually a little bit worse than you get at room temperature. And this problem is the power dependence. Due to this non-linearity, you convert AM to PM noise through a factor of 1,000 times coefficient due to this non-linearity. So when you change the power in your experiment, you get a huge change in frequency. So this is the limit. And this is the limit of these quartz resonators, where a sapphire can take loads of power before you get any frequency shift. So we measured these, the noise, and we verified that the noise level is consistent with this frequency instability due to power fluctuations. So what is the answer? And here's a publication we show when we can use the non-linearity to generate a comb. So here we are at low temperatures, and when we excite modes in this phonon resonance, because of the non-linearity, we generate a comb. It's sort of like a comb you get at optical frequencies, and that is non-linearity is what's the problem. You can see here as we make the power, as we read out the resonance with the higher power, there's this dumping non-linearity, and then this active regime where you generate sidebands. That is summarize the problem. So what we're trying to do is we're going to try and build an oscillator with a squid amplifier, so we can oscillate at a much lower power and then amplify with a HEMT. And this might be a way to generate a much lower noise using a quartz oscillator. You can use the quartz in a passive mode where you just read it out and you see the thermal noise. And in this regime, it's linear because there's no duffing non-linearity. You're just measuring the Nyquist noise fluctuations. And in this regime, you can make the full use of the 10 to the 10 Q. So this is just like, this is like a gravity wave detector, a little gravity wave detector. And we can use this to do some tests of fundamental physics. So as far as scalar dark matter goes, these type of experiments where looks like a gravity wave detector for search for dark matter were proposed. And you can see that our quartz results here, the Auriga detector and the Brazilian spherical detector. There is a problem though. Our Qs are much narrower than the dark matter halo line width due to virialization. So we do not know how to make use of our high Qs to measure scalar dark matter because it will just look like a broadband noise compared to the line width of our Qs. So that is a problem that we have. We have to somehow try and increase the bandwidth. In Auriga, that was done through a multi-mode system, which could increase the bandwidth of the system. So I don't know how to use our data to look for scalar dark matter at the moment. Here's another paper which proposed these type of experiments, and we have our quartz bores here, and they wanted to use sapphire cylinders. But these will have the same problem, because the sapphire is very high Q, it will be too narrow band to be able to see. It will be able to see cold flows of dark matter, but not the the halo. Then we have axions, which we also are looking for, which I can tell some of our work on axions. We have our oscillated and resonator group axion experiment, which has just started to run. The first experiment uses one cavity. The idea is to use multiple cavities, and the reason why we call it organ. We did our first run in 2015, where we showed a prototype experiment with no scanning. And now our first phase began last month, and we are now taking data. We have this large fridge with a 12 to 14 Tesla magnet, depends how you ramp it, whether it quenches or not. But we have our experiment in this Blue Force system, and we have a cryogenic translation stage to tune the cavity. We're also researching detection mechanisms based on Joseph's junctions. We want to use single photon detectors. If we can develop them, we'll get a huge improvement. So we've started phase 1A, which is, this is a diagram of the phases that we will run. We've started this scan here. We've started at around 15 gigahertz, and we're now completing this scan, which will test this cogenesis theory. Axions can exist up at this band, and QCD axion exists there. Eventually, we want to get here. We have a plan to do that, which I won't go into today. We've also built this AC haloscopes, where you have two modes where one acts like a modulation field on the other to detect an axion, and it looks like this instead of a DC field like you have in an axion haloscope with a microwave cavity. You have two AC fields, and then your axion can be at the sum or difference frequencies. So this was built, and two modes which exist, which can be sensitive to these type of axions. You have to have a TE and TM mode, which have non-zero overlap. And we build these two, we put the two modes in the one cavity and make two oscillators. We have our pump oscillator, which should have a large power, and our readout oscillator, which should be lower power. And therefore, any axion will imprint itself onto this as a sideband. And this is our phase noise measurement readout, which is a discriminator. So that measures the frequency noise. We measure the frequency noise in the system, and we search for signals at plus or minus the Fourier frequency. And the axion will imprint it as a sort of bump on the spectral density due to its line width. And we put sensitivity limits in our first measurement, and now we're looking at improving this, and we're looking at comparing the frequency to two different schemes, one which will generate a power signal and one which will generate a frequency signal. Now.
Mike, you have 10 minutes to go. 10 minutes.
How many minutes?
10 minutes, including time for questions.
Oh yeah, no problem. Thank you. We're also looking at Lorentz invariance experiments in the phonon sector, which are Lorentz violations, which are due to mass, because it's a massive vibration, and you could get variation in the frequency due to that. With Berkeley, we did the first experiment in their rotation system, and we got some limits on Lorentz violating parameters. We improved the system in our lab by 2 orders of magnitude, and we have our rotation system here, which is shielded, which Maxime built, and now Cindy is a new postdoc which is analyzing the data. We've got 2 years of data, and we have these runs which ended up having good data to include for the analysis. We expect to see these sidebands, and there's all these standard model extension coefficients, and this is the data. We have our systematics at twice the rotation frequency and single rotation frequency, but we look for offsets around this. And looking for those offsets, here's some example of the noise for different frequencies, and this is compared to sidereal offsets, and they're on the order of 10 to the minus 16, as we predicted. So once we finish analyzing this, we'll have new bounds on these parameters. And then we hope to go to the non-minimal sector. We have the help of Matt Muse, who worked out the theory of this to put those limits. And we also can test quantum gravity. We did an experiment with acoustic system. This was published a couple of years ago. And there should be a change in the commutator relationship, like I mentioned at the start. And the Bohr and the Sapphire acoustic resonators were used to put these limits. And a future experiment can get to a level where we might expect to see a signal. That's all I will say about that. This is our Sapphire acoustic oscillator. It's like a dumbbell. At the moment, Pavel has that, but we're thinking of bringing that back to Australia to do the measurement here. Because he's now focused on quantum computing, like lots of the world, or you can use these Bohrs as well. The last I will just mention, I have time to mention our work on high frequency gravity waves. This is almost accepted. Hopefully it's with editors, hopefully it's going to be good. It was pretty good last time around, and hopefully the reviewer liked our last modification. So we wrote this paper, Maxim and I wrote this paper that these acoustic crystals are sensitive to gravity waves back in 2014, and we gave values of the strain sensitivity depending on based on our measurements of 4K and millikelvin. So at 4K we could do 10 to the minus 21 times something, and we could get better than that millikelvin. So this is the way it looks. We just a couple of squid and we read out the vibrations, and you can see the thermal noise. We were recently part of a consortium that looked at the challenges and opportunities for gravitational waves at megahertz to gigahertz frequencies. And you can see here there's some predicted noise sources around where our bulk acoustic waves can look. Don't ask me about the predicted noise source. So what we did, we got this running and we ran it for 153 days, all completely shielded, copper enclosure and a niobium shield. And we just had one device. It was our first measurement. And over these 153 days, we saw 3 events. Eventually, we only mentioned 2 events in the paper because Seong, who's from Glasgow, thought this wasn't significant enough, but these 2 were, once we done to say that we had some events. We're not claiming they're gravity waves, we're just saying we saw some events. And what those events are interesting. So now that we've seen these events, we have to do a better job. So we're now building 3 separate cavities, detectors like this, and they're going to be orientated in different ways and in different places. And also we will monitor different modes. So here in the first run, we monitored the mode at 5 megahertz and 8 megahertz. And when we saw this event, it only occurred in the 5 megahertz mode, not the 8 megahertz mode. So after that, once we got it rerunning, we thought we'll make the second mode closer to 5 megahertz. So we had a 4.99 megahertz and 5.5. And then we saw 2 more events, and they happened in both modes. So, so whatever the process is, it's localized around this frequency, and it's probably some impulse event or something like that. It could be anything. It's on the archive, this paper. That's not the latest version after the reviews, but it could be anything from internal solid state process to maybe a cosmic ray or internal radioactive event to a high frequency gravity wave, a domain wall, WIMP or whatever. Who knows what they are? Our next goal is to get a whole lot of these running and see what we measure. That's the end. So now I can take questions.
Thank you very much, Mike, for the very nice talk. Indeed, question time. Well, if no one has any questions, I actually have just a quick comment that with the scalar DM searches, scalar dark matter searches in the audio frequency band, there is also a new result now with the large-scale optical interferometric gravitation wave detectors. And on Thursday, we'll have a talk from Sander Fermionic. He's from the GS600 collaboration, and they currently have the most stringent bounds on these types of interactions for the dark matter search. So maybe I can even send you the paper. So the bounds are somewhat more stringent than some of the plots that you've shown.
Yeah, that's great. I would like to see that. Yeah, please send me.
So are there any scientific questions to Mike?
I guess we might as well continue on then.
So that means it was a very clear talk. Thank you very much.
No worries. I'll stop sharing screen.
So thank you very much to Mike. Our next talk is by Vladimir Tyuba from Sydney. Vladimir, if you'd like to share your slides.
I need to find them.
Oh, perfect.
Is it right slide?
It's the correct slide. It's the title slide, and I can see your pointer. Excellent. So whenever you're ready, please.
Okay, thank you very much. I would like to thank the organizers for the opportunity to present our work here. This work is done with, in collaboration with Jugan Gli from Beijing, China, and with Stefan Ulmer from Germany. I would talk about atomic clocks sensitive to variation of the fundamental constants. The motivation for this work is very simple. Manifestation of any new physics at low energy is expected to be small, which means that very high accuracy of measurements is needed. And the highest possible measurement accuracy of the measurements is achieved for atomic optical clocks. For example, for ytterbium, fractional accuracy is on the level 10⁻18. Optical frequencies depend on fine structure constant alpha. New physics may manifest itself via apparent variation of alpha. Therefore, we need to find atomic clock transitions which are sensitive to variation of alpha. Dependent atomic frequencies on alpha can be in the vicinity of physical value of alpha, which is alpha 0, can be expressed via this formula, where Q is sensitivity coefficient. Q can be found only from atomic calculations. There is no simple analytical formula for it. And in computer calculations, Q is found by varying the value of alpha in computer codes and taking numerical derivative. To measure atomic frequency, or to measure anything, we need units. And in case of optical frequencies, the best choice is just to take another optical frequency, because nothing can be measured to better accuracy than frequencies of atomic clocks. And if we measure dimensionless ratio of two frequencies of two different transitions, then it can be linked to variation of alpha by this formula. There is a difference between two terms expressed like 2q divided by omega. This is usually called enhancement factor. So to get the highest sensitivity of atomic clocks to variation of alpha, we need two transitions with two big and different values of enhancement factors. And enhancement factors can be positive or negative. Non-relativistic limit corresponds to k equal to 0. So how to get large values of enhancement factor? There is obviously two ways: to have large Q or to have small frequency. And there was a large number of works looking for large enhancement factor due to small frequency. But actually, we come to conclusions that looking for large enhancement factor due to small frequency is the wrong idea, because accuracy of the measurements is equally important, and real figure of merit in the search for high sensitivity to variation of alpha is this ratio of enhancement factor to relative uncertainty of the measurements, and this ratio does not depend on omega at all. So to further illustrate this point, it is useful to consider extreme example, dysprosium atom. Dysprosium atom is a unique system. It has two levels of different configurations, which has practically the same energy. Actual interval between these two states is due to isotope shift and hyperfine structure. And both states have relatively large values of Q, relativistic energy shift. Enhancement factor is of order of 10 in power 8. This is huge value. It actually depends on which hyperfine structure components or isotope are used. And dysprosium was actually used to put limits on variation of alpha. And here a result taken from this paper. And it can be compared with other measurements, including most recent, most accurate measurements done in two different transitions of ytterbium plus. And we can see that all results are of the same order of magnitude. So this huge enhancement brings no benefit. Actually, dysprosium system is still good, but not because of huge enhancement factor, but due to large values of Q. In all other systems, this value of K enhancement factor is of order of 1. For example, for ytterbium plus, there are two clock transitions. For one, enhancement factor is close to 1 and another close to -5. So this means that we should look for large Q regardless of the value of omega. And to see how to find this, it is useful to consider this analytical formula, which represents relativistic energy shift. It is approximate formula. It comes from considering electron to be in Coulomb field, because relativistic effects comes from short distances from nucleus where potential is close to Coulomb potential. And in this formula, C simulates exchange interaction and other many-body effects. Its numerical value is of order 0.6. We can see that we can have large energy shift if E is large. So it can be found in highly charged ions. Another important thing is large Z. So we should consider heavy atoms. And also, not so obvious thing is that we should look for large delta J. We should look for the difference. Omega of transition is the difference between energies of two states. So the value of Q will be is given by the difference of energy shift of two states, and having large delta J is important to avoid cancellation of relativistic effects in this difference. So E can be large, Z can be large, but if J are the same in both cases, this value could be small. So this last condition is very important. Then interesting question is whether we can have all three factors of enhancement, and the answer is yes. This diagram represents where highly charged ions sensitive to variation of alpha can be found. Here is number of electrons and here is number of protons. Diagonal represent neutral atoms, and this distance from shaded areas to diagonal is ionization degree. So here in these large areas we have highly charged ions with 5p for F transitions or 5s for F transitions and so on. And there are many of them. Here we can start from 1 electron on 4F subshell and add electron by electron and go to higher Z simultaneously and up to 14 electrons. So in total, we have about 100 of such ions, which all have optical transitions sensitive to variation of alpha. And there are many transitions which have all features of optical clock transitions. So accurate measurements are possible. And these systems are studied experimentally, for example, in RIKEN in Japan or in MPI in Germany. But progress with highly charged ions is slow, and there are serious reasons for this. For example, there are many experimental problems. All these ions practically not studied. There is no experimental data for them, apart from some frequencies of M1 transitions between states of the same configuration. These systems have no strong optical electric dipole transitions, which would be the easiest to measure, which means that what is needed can be measured, all are very weak transitions. And there is also very poor support from theory to guide the measurements. And theory has also its problems. Atomic frequency of the transitions, which we want to be in optical region, are found as a difference of huge energies of ionization of the ions. And we are interested mostly in transitions between states of different configurations. Different configurations means that uncertainty of the calculations for each energy is different, and there is no cancellation because of this. So the difference in the uncertainty, total uncertainty in frequency of the transition is the order of the frequency itself. So accurate calculations are very difficult, and there is no experimental data to test the methods or to build some semi-empirical methods to fit the data. It is still promising area of research, but more efforts are needed. So today I will be talking about different systems. We focus on optical transitions in neutral or nearly neutral systems with large Z and large delta J. And these transitions must also have all features of optical clock transitions. Corresponding criteria formulated by Katori, for example. This must be optical transitions from ground to some metastable long-living state. Transition is not sensitive to perturbations like black body radiation, shift, Zeeman, star shift, and so on. And there should be other transitions relatively strong, which are needed for detection, for cooling, and for other purposes. So we studied many such systems, and here is a almost comprehensive table for atomic clock transitions in neutral and almost nearly neutral systems with large values of Q, with one exception. Ytterbium, working clock for ytterbium is presented for comparison. In this table, working systems are shown in green, like this ytterbium clock transitions and ytterbium plus. Ytterbium plus currently is the best working system, which has two transitions, both quite sensitive to variation of alpha. In contrast, this clock transition in ytterbium is not very much sensitive to variation of alpha. There was also mercury plus, but work with this ion is stopped to the best of my knowledge. And in red, we show new proposals for clock transitions sensitive to variation of alpha. I would like to add that it is important to, or at least very convenient, to have two transitions in the same atom. So one transition can be measured against another without changing apparatus, changing systems. And in ytterbium, there is another clock state which is sensitive to variation of alpha and can be measured against working clock transition. In gold, we found two metastable states which are both sensitive to variation of alpha. And we see that Q coefficients are large for both states. And if we measure one transition against the other, it will be the most sensitive system for variation of alpha among neutral systems. Only ytterbium plus might be better. So let's consider in little more detail both examples. Here is energy diagram for gold. Here we have one optical clock transition from ground state to first excited state. And there is another metastable state, which can also be used as clock state. We suggest as clock transition between first clock state and another to have more convenient frequency of the transition. But probably transition from ground state can also be considered. It is important that there is a transition which can be used for cooling. This is strong E1 transition. There is possible linking from this state, but it is suppressed due to the fact that these states differ by states of two electrons. So electric dipole transition, which is one electron operator, can go only via configuration mixing. But in any case, repumping is possible here. We also studied sensitivity to different perturbation and found that it is transitions are not very sensitive. They are as good as most of other clock transitions. And here is energy diagram for ytterbium. This is walking clock transition, which where the very high accuracy of the measurements is achieved on the level 10⁻18. And there are two more metastable states. This is most sensitive to variation of alpha, and it is more long-living than this one. So it is probably the best choice. So we can measure this frequency against already working clock frequency and achieve very high sensitivity to the variation of the fine structure constant. It is important also that this is already working clock, so we don't need to consider cooling detection and many other questions. All new clock states have large J, and in principle, it is some kind of problem because it makes them more sensitive to some high order perturbations like quadruple electric shift, which is not possible if J is equal to 0. This large value of J is unavoidable because we are looking for transitions with large value of delta G. And it leads to, if one clock state have J equal to 0, then due to this condition, another clock state has to have large J. And how to deal with these problems? And it turns out that there are ways to go around this. It can be different with different specific examples. For example, if we have clock state in ytterbium with J equal to 2 and with no hyperfine structures, then quadruple shift is given by this formula. And from this formula, we can see that its value is the same for Jz equal to 0 or Jz equal plus minus 2, but value is the same by sign.
You have 10 minutes to go, 10 minutes.
Okay, that's good. So the electric quadruple shift and linear Zeeman shift can be suppressed simultaneously by averaging between transitions with Jz equal to 0 and Jz equal plus minus 2. For gold, the picture is slightly different. For gold, there is only one stable isotope with nuclear spin equal to 3½ and we have two clock states with J equal 5½ and 9½. And therefore, we have this range of total angular momentum 1, 2, 3, 4, or 3, 4, 5, 6. And quadruple shift is given by this formula. We can notice that if we consider F equal to 3, which is possible for both clock states, and Fz equal to 0, Fz equal to 2 plus minus 2, then this factor is exactly 0. So quadruple shift can be avoided this way. And linear Zeeman shift can be suppressed by averaging between transition with Z equal plus 2 and minus 2. Now, there are more searches for new physics where several transitions in one system can be useful. One is search for new physics in king plot, which was already mentioned several times on this conference. King plot is a way to link two isotope shifts in two different transitions in one formula. And this first line is the standard formula for king plot. Here is isotope shift, this reduced mass, this electron structure factors, this electron structure factors for mass shift, this electron structures for volume shift. So if we take this plane, one isotope shift against the other, then this represents straight line. Every pair of isotopes represent a point on this plane, and all of them, according to this formula, should be on the same line. But if we have extra terms in this formula, for example, due to interaction with extra boson, then this term breaks linearity because this factor depends on isotopes. It will be different for different isotopes, meaning breaking of linearity. And actual king plot may look like these points which are not on the same line. And using this deviation from straight line, we can put limit on this term and limit on extra interaction. The work is in progress for ytterbium compared to ytterbium plus, and corresponding talk was presented yesterday by Demis Antipas. More new physics. If we, where comparison of clock frequencies can be used. For example, if we consider scalar term in standard model extension Hamiltonian, which depends on gravitational potential, then this term must lead to variation of frequency during the year. It should have, because of variation of gravitation potential of the sun due to variation of the Earth-Sun distance, and it should have maximum or minimum in January and in July. Interpretation measurements here should be exactly the same, but interpretation is different. And what is important to notice here is that sensitivity is due to relativistic effects, and it is very similar to variation of alpha. So all systems which are sensitive to variation of alpha should be also sensitive to this term, which depends on gravitation. And there was an interpretation of some measurements which help to put limit on the strength of the interactions, and there are also more recent limits obtained in one of them just this year, and there will be a talk by Peik after tomorrow to present details. There is also tensor term is standard model extension Hamiltonian, which lead to different effects. Is dependence of atomic frequencies of the Earth rotation. As Earth rotates around its axis, frequency of transition between states with different projections change compared to each other. Here we need to have metastable states with relatively large values of total angular momentum, greater or equal to 1. So new states in ytterbium and gold are good candidates for these measurements. There were a lot of activity around this. I have no time to describe them, so I can directly to conclusion. New clock states in ytterbium and gold bring new opportunities in search for new physics, such as alpha variation, new boson, Einstein equivalent principle, and local Lorentz invariance variation, and so on. Thank you for your attention.
Thank you very much, Vladimir, for the very nice talk. Are there any questions? Oh, Eckhard, please.
Hello, Vladimir. Yeah, could you please explain the last point about the additional yearly dependence of the frequency again? So the experiments have been analyzed so far in terms of coupling of the fine structure constant to the gravitational potential. But I understand that the term that you are analyzing here is different. Could you please explain that again?
For some reason, I cannot move back to.
I think if you click on the bottom left, okay, maybe easier just to go directly to the slide with this, yes.
Do you mean this slide?
Yes, yeah.
This term contains gravitation potential. In our case, we consider gravitation from the sun. Since distance between Earth and Sun varies, potential varies, the value of this term varies, and so does the frequency of transition.
Okay, but this would be equivalent to a coupling of alpha to the gravitational potential, or is it different?
They can be connected. Yes, so this variation of frequencies can be expressed in terms of variation of the fine structure constant. When we are talking about variation of fine structure constant, we actually don't specify a reason for this. It can be anything, including gravitation field, interaction with dark matter, and so on and so on. This is when we talk about variation of alpha, we just consider a very general approach. And then we can adopt a different approach when we consider specific reasons for atomic frequencies to vary.
Mm-hmm. Okay,
and this is one of them.
Are there any other questions? If not, let's thank Vladimir again. And our next talk is by Masao Takamoto from Tokyo. Masao, if you would like to share your slides, please. Oh, excellent. Whenever you're ready.
Okay. Thank you for your introduction. I am very pleased to have an opportunity to give a presentation at this conference. First, I'd like to thank the organizers for the invitation to this conference. I'm Masao Takamoto, research scientist from RIKEN. Today, I'd like to talk about the test of gravitational redshift with optical lattice clocks and their applications to relativistic geodesy. So, okay. I'm sorry. I'd like to start by giving a brief overview of optical lattice clocks. Optical lattice clocks has a potential ability to achieve accurate and stable clock operation at 10⁻⁸ level. Optical lattice potential confines billions of neutral atoms in separate microtraps. Then this strong confinement suppresses atomic thermal motion and it allows Doppler-free spectroscopy. And also by tuning the lattice laser to the magic frequency, we can realize a light shift-free confinement at the lowest order. And also by probing a large number of atoms at one time, that improves the stability of the clocks, which is proportional to 1/√n. So the optical lattice clocks can reach 10⁻⁸ level, which is 2 orders of magnitude higher than the accuracy of cesium clocks that defines a second, can be achieved in a short averaging time by averaging large number of atoms. So actually in 2015, we have realized the uncertainty of 10⁻⁸ level with our cryogenic optical lattice clocks. In this work, we have demonstrated 2 clocks agree within the uncertainty of 10⁻⁸ level. And recently, several optical clocks has achieved 10⁻⁸ uncertainties or below with optical lattice clocks with strontium and ytterbium and ion clocks with aluminum and ytterbium ions. So what is the application of such high accuracy of optical clocks? One is the relativistic geodesy. So according to the Einstein's theory of general relativity, a clock in a higher altitude ticks faster than one in a lower altitude due to gravity. So height difference of 1 centimeter causes time dilation of 10⁻⁸. So the accurate clocks become the precise probe of such gravitational potential. And the clocks becomes a system of elevation that defines the equipotential surface, which can be called quantum benchmark. So firstly, to demonstrate such relativistic geodesy, we firstly demonstrated frequency comparison of remote optical lattice clocks in RIKEN and the University of Tokyo in 2016. So this is the observed results. Blue line shows the frequency difference between the clocks with same height, which is consistent with 0. And the red curve is the frequency difference between the clocks in University of Tokyo and RIKEN, which has altitude difference of 15. So we can observe the altitude difference between Riken and the University of Tokyo in real time by clock comparison. So this data is in good agreement with a conventional leveling survey, which is performed by Geospatial Information Authority of Japan. So we have realized the laboratory-based fixed point measurement of the gravitational potential. So to further expand its application as a measurement tool of gravitational potential, the clock system needs to be transportable. So we started development of transportable setup. This is the old system, laboratory-based optical clocks. We have used 18 frequency stabilized lasers, which is required for the operation of 2 clocks. So the system only works inside the laboratory. So as a practical tool for the measurement outside the laboratory, we develop a more compact and transportable setup. And such transportable clock was also demonstrated by PTB in 2017. So this is our transportable optical lattice clocks. So left one is the main spectroscopy chamber, which is set inside the magnetic sealed box with 60 centimeter cube. So for the cooling lasers, we have developed laser welded compact external cavity diode lasers. And these lasers are installed inside a 90-inch rack mountable laser box with other related optics. So this is a schematic diagram and the sequence of the clock operation. To operate optical lattice clocks at 10 to the minus 18th level uncertainty, we have to carefully reduce the uncertainties which comes from the black body radiation shift from the environment and the lattice light shift. So for these purposes, we have developed a one-dimensional optical lattice with a ring cavity which enables transport atoms inside the BBR field. The operations of the clocks is as follows. Firstly, we load atoms into the lattice at the center of the chamber. Then we transport atoms into the BBR field by applying a moving optical lattice. And inside the BBR chamber, we excite the clock transition. This BBR field is temperature controlled by a Peltier element at 240 Kelvin. Then we transport atoms back to the outside and measure the excitation rate. Then we apply feedback to laser frequency to keep resonant to strong transition. And we repeat this cycle every 1.6 seconds. And this is a pair of transportable optical lattice clock setups. The laser system with controlled electronics are all mounted on 19-inch racks. So the laser box 1 include cooling laser and pumping lasers. The laser box 2 include narrow line cooling and lattice laser and clock lasers. And both clocks are connected by a noise-cancelled telecom fiber to send cavity stabilized reference lasers at the subharmonics of the laser distributor. Then the frequency difference of 2 clocks is measured to determine the gravitational potential difference. firstly, we performed a preliminary experiment in the laboratory environment. We firstly measure the height difference of 1 meter by comparing two clock setups. We lift up one of the clocks by 1 meter and compare their clock frequencies. Then we measure the gravitational redshift for 1 meter height difference. This is the frequency difference of two clocks. With the same height, the frequency difference is consistently 0, which means that both clocks ticks with the same pace. Then if we lift up one of the clocks by 1 meter, we can clearly resolve the gravitational redshift for 1 meter with an averaging time of 8 minutes. So time duration for 1 meter height difference due to general relativity is resolved by comparing optical lattice clocks with a few minutes of averaging time. Then we scaled up the height difference from 1 meter to 450 meter. We transported our clocks to Tokyo Skytree, a broadcasting tower in Tokyo. Then we performed a test of general relativity. A pair of clocks are set at 0 meter and 450 meter floor. Then we connected these two clocks with an optical fiber link and measure the gravitational redshift for a height difference of 450 meter. So the height 450 meter height difference corresponds to a gravitational redshift of about 21 Hertz according to the general relativity. And if a pair of clocks are compared with the uncertainty of 10 to the minus 18th, the general relativity can be verified with the accuracy of 10 to the minus 5th. And we also measure the height difference of two clocks by laser ranging and global navigation satellite systems, and measure the gravity by gravimeter. Then we combined these results and we evaluate whether alpha is consistently 0 or not to test the general relativity. So such kind of test of general relativity was firstly done by pound replica Snyder experiment in Harvard Tower with a height difference of 23 meters. So in 1960, so this experiment gives an uncertainty of 10 to the minus second. And after that, gravity probe emission in NASA has tested general relativity using a hydrogen measure in a spacecraft with a height difference of 10,000 kilometers in 1980. And this gives an uncertainty with 10 to the minus 4th level. And recently, ESA project tested general relativity using atomic clocks on satellites on elliptic orbits with a height difference of 8,500 kilometers. So these results report new constraint at the level of 10 to the minus 5. So here we demonstrate a test of general relativity with a ground-based experiment using accurate clocks with 10 to the minus 18th uncertainty. So We firstly installed 2 clocks in Tokyo Sky3 in October in 2018. The period of the experiment is until April 9th in 2019. So these photos shows a pair of optical lattice clocks set at 0 meter and 450 meter floor. A pair of clocks are connected by optical fiber link with a length of 700 meter with a fiber noise cancelling system. So operation of both clocks are automated with remote access. And even with a relatively large diurnal environmental temperature change of 10 degrees Celsius, we have realized a stable operation during the experimental period. This is a schematic of whole measurement setups. The graphs on the left side are the spectrum obtained for the clocks at 0 meter and 450 meter. So the gravitational redshift of 21 Hertz is observed for the height difference of 450 meter. This gravitational redshift is accumulated by stabilizing the clock laser to each spectrum. On the other hand, the height difference of 2 clocks is measured by 2 ways of survey. One is the height measurement using a GNSS. The DNSS antenna is set at 0 meter and 458 meter, and the short distance is connected by spirit leveling. The other way is laser ranging. So laser ranging was performed by laser distance meter through non-aperture near the central pillar of the tower. So 4 divided parts are measured continuously to determine the height difference. Then finally, combining the results of redshift and the height difference, we evaluate the parameter alpha. This is the result of the measurement. So firstly, the DNSS measurement was conducted for 5 days for each data in October. The result agrees with the simultaneous laser ranging measurement within the uncertainty, so which validates the consistency of the height measurement. After that, laser ranging continuously monitors height difference. The data shows shrinking of the tower by 5 centimeters, which corresponds to the seasonal change in the outer temperature of 10 degrees Celsius. Then finally, we performed a clock comparison and measure the gravitational redshift, which is shown in the middle graph. The gravitational redshift was accumulated for 1 week. This data was compared with the height difference measured by the laser ranging by assuming alpha to be 0, then which shows a consistency within the error bar. So the last panel is a bit note of 2 clocks set at the same height in beacon. The data shows reproducibility of the clocks at the uncertainty of 10 to the minus 18. Then this is a summary of the result. The height difference measured by GNSS and laser ranging are consistent within 2 centimeters, which is less than the uncertainty of the measurement. The height difference is measured by laser ranging with 13 millimeter uncertainty, which was compared with the gravitational redshift measurement by the clocks with an uncertainty of 4.3 times 10 to the minus 18th uncertainty. Then we have derived the parameter alpha to be 1.4 plus minus 9.1 times 10 to the minus fifth, which improves the ground-based clock comparison by an order of magnitudes and is comparable with the space experiment. After the experiment in the Sky Tree, we are now developing a transportable optical lattice clocks on Pico. So development of such on-vehicle setups allows us to realize a gravitational potentiometer that can operate in any location. Using a 1,000 kilometer scale long optical fiber link, we apply it to monitor cluster movement and tidal effect at the 10 to the minus 18th level.
Masaosan, you have 10 minutes to go.
Okay.
10 minutes.
Thank you very much. So one of the clocks, slave clocks used in the Sky Tree experiment was modified to be mounted on the Pico. So the wagon was remodeled by Icing to load 3 90-inch racks inside. The clock can be operated inside the wagon by providing power supply. Then by connecting optical fiber to transfer the clock frequency, the clock can be compared with the reference clocks. So this is the overall view of the clocks inside the wagon. So we have 3 racks. One includes laser source for spectroscopy, and the other one has a UHV chamber for spectroscopy and the related controllers. And the third one has the laser sources for atomic cooling. So then we operate the clocks inside the vehicle. The clock transition is interrogated by laser pulses with a free evolution time of 400 milliseconds. The laser is supplied from the master clock in the laboratory. So to check the performance of the clocks, we have compared the clocks on the vehicle and the clocks in the laboratory through an optical fiber link. The vehicle clock is set on the ground, which is 5 meters higher than the laboratory clocks in the downstairs, and which is connected by a 20-meter long optical fiber. The frequency difference are shown in this graph. Blue plots show the frequency difference between the on-vehicle clocks and the laboratory clocks. And the red one shows the both clocks in the lab. So we can clearly resolve the gravitational redshift without averaging. So this is a summary of the measurement. The height measured by the laser lensing is consistently with clock comparison with centimeter level precision. This is the around deviation of the clock comparison. The blue dots show the frequency difference between the on-vehicle clocks and the laboratory clocks, and red one is the around deviation for the clocks both in the laboratory. So we have no big difference, so the vehicle clocks has no degradation by loading on the vehicle. So the around deviation reaches 10 to the minus 18th with an averaging time of 3 hours. So which is faster than the height measurement using GNSS, which requires almost 1 day of averaging time to reach 1 centimeter uncertainty. And this around deviation shows that the comparison resolves 80 centimeter height difference in 1 second averaging time in real time. And now we are preparing a long distance fiber link from Tokyo to Tohoku area. In Tohoku, there is a VLBI astronomical observatory in Mizusawa Esashi, which is 500 kilometers away from the Riken, and fiber length is roughly 800 kilometers. So we plan to transport umbilical clock to Mizusawa Esashi and compare with reference clocks in Riken using a long distance fiber link. Then we will measure gravitational potential variation for geodetic applications. For example, slow uplift of the ground after the earthquake in Tohoku area, which is called post-seismic relaxations. So this is a summary of my talk of 2 topics. Thank you very much for your attention.
Thank you very much for the nice talk, Michal. Are there any questions? I actually have a question. With the transportable clocks, do they have to be stationary when you take the measurement, or can they be on board moving vehicles? Or is it too difficult to have the height stabilization to have very accurate measurements on a moving vehicle?
Yes, now in our setup, we have stationary environment, so we cannot drive a car during the measurement.
Is that something which you can potentially do in the future?
Yes, but anyway, we need a fiber link, so it's not maybe so easy.
Okay,
Yes.
I understand. Thank you. Are there any other questions? If not, let's thank Michal again for the very nice talk. And our next speaker is Carlos Martins.
Yes, hi.
If you'd like to share your slides, please.
Here we go. That should work.
Oh, perfect. Whenever you're ready.
Right. So, hello everyone. Thanks very much. It's a pleasure to be here, even if it's just virtually. So yeah, I'd like to discuss a little bit a few things we've been doing in Porto together with other collaborators. So let me start with a very brief introduction / motivation. So I'm a cosmologist. So my starting point is the observational evidence for the acceleration of the universe. What that shows us is that our canonical theories of cosmology and particle physics are at least incomplete or possibly even incorrect. So there's new physics out there waiting to be found. And therefore, astrophysical facilities should aim to search for, identify, and characterize these new physics. So this is what we do in our team. So the Espresso project, we use precision astrophysical spectroscopy and various other tools to try and address some grand challenging questions, such as what makes the universe accelerate, are the laws of physics universal, and so on. So, and we aim to cover both theory and data analysis, and we are also involved in the building of next generation instruments, particularly for ESO, the European Southern Observatory. And we also pay some attention to education and outreach. That's sort of off topic for this morning, but I'm happy to tell you what we do some other time. Okay, so if we're searching for new physics, it would help to have an idea of what this new physics might look like. And of course, we won't know exactly until we find it, but a good starting point would be scalar fields. We know that scalar fields are among nature's building blocks. We know that the scalar fields, if you put them in your Lagrangian, will typically couple to all the other degrees of freedom in the model, unless you postulate some symmetries to suppress these couplings. So you should expect to find, if these things are there, at some level, long-range forces and so-called varying fundamental constants that we are discussing. In particular, couplings to the electromagnetic sector will lead to space-time variations of fine structure constant, which is useful because it can be tested in a number of different ways, as all of you know. So this is a very broad topic. I don't have time to cover all of it. I can just shamelessly advertise a review I wrote a few years ago. It's actually a bit out of date now. The field has been progressing a lot, but it might still be a good starting point if you want to get into the subject. Okay, so I want to cover three different but related things. So let me start with the first one, which is direct astrophysical measurements of alpha and other dimensionless couplings. So here's one slide sort of summarizing the current status of all measurements. So we have measurements of alpha, measurements of mu, the proton to electron mass ratio, and also measurements of several products of alpha, mu, and the proton gyro magnetic ratio, GP. So these measurements probe different redshift ranges with different sensitivities and so on. And there's also, of course, a lot of scatter, as you can see, just looking at the plots. If you try and sort of naively do a joint likelihood analysis of all the data, taking all the error bars at face value, you find 1 to 2 sigma preferences for variations for non-zero values. So not very strong statistically, but there's also a limiting factor, which is we know, specifically in the case of alpha, that systematics of current spectrographs are around the 3 part per million level. So clearly we need to get more accurate measurements with more sensitive instruments. So I'll come to that point in a second. But another way to go forward is also to try and do these direct measurements at higher redshifts. The argument being, if you have a scalar field moving slowly, it's easier to detect these slow variations with a bigger redshift level arc. So if you go to higher redshifts, deeper into matter era. And if you want to do that in the case of alpha measurements, then you need to do measurements in the infrared as opposed to the optical. And one of the things we've done recently with various different collaborators, including John Webb and his group, is to notice that data from a high redshift quasar at redshift 7, initially published by Mortlock et al. In 2011, can actually be used to provide direct measurements of alpha in the redshift range between 5.5 and 7. As opposed to the previous highest redshift direct alpha measurement, which was at a little bit above redshift 4. So for this, we rely on 30 hours of data of the X-shooter spectrograph with a resolution of 7 to 10,000, which is a bit low compared to optical measurements of alpha, but it's the best one that we can do right now. So this leads us to these first alpha measurements in the infrared and the highest redshift measurements, direct measurements of alpha so far. So these you see on the right side of the plot. So the 4 gray ones are the measurements in 4 different absorbers along this line of sight. The black one is the weighted mean combined result of all 4. So you see the error bars are significantly large compared to the optical measurements at lower redshifts. But this is a proof of principle. It shows that one can do this in the infrared. It's just a question of finding the sources and having better data. In terms of finding the sources, I think the prospects are actually quite good, given what we know about the distribution of quasars as a function of redshift and so on. We estimate that there could be about 30 or so high redshift quasars out there for which alpha measurements would be possible, and in some cases with better sensitivities than the current one, which is at the 72 part per million level. So I think this is very promising. In some cases, data on some of these quasars may already be lying in some people's hard drives. So it's a question of searching through archives, re-observing some of these sources if necessary, and doing the analysis. So I think that this is a good prospect for the future. Now, coming back to more precise measurements, we have the Espresso Spectrograph, and this is what it looks like. Is also the background you see behind me. It's actually a little bit unfortunate because the spectrograph itself is inside this tank. It's a vacuum vessel, so you get a stable temperature and pressure conditions. But so the spectrograph has been built. It's now operational at the VLT in Chile, and we're taking data. We're of course been slowed down by COVID, as many other people. So results are not out yet, but they should be coming out soon. So before the results come out, here's a slide with some technical specs of the spectrograph. This might not be of interest to some of you, but it might be of interest to others. So I leave it here just for reference. What might be more interesting is what we plan to do with the what's called the guaranteed time observations that the consortium has in exchange for building the spectrograph and providing it to ESO and to the rest of the community. So this is our initial plan. It has had slight tweaks given COVID and other things, but broadly it's still applicable. So we want to do direct measurements of alpha in 10 or so different lines of sight. We want to do some direct measurements of the proton to electron mass ratio, mainly through molecular hydrogen, possibly also CO, carbon monoxide. We want to do some direct measurements of the CMB temperature at redshifts around 2 or 3. We want to measure the primordial deuterium abundance, which is important for nucleosynthesis. And we might explore a few other ideas, such as doing a preliminary test of the feasibility of the redshift drift, which is one of the science drivers for the next generation ELT. Okay, so this is what I can say about Espresso for today. We have data, we are writing some papers, we have 2 that are more or less finished, and then it's a question of submitting them, getting green light from the referees and so on, but hopefully you'll see the first results out in not too distant future. Okay, so let me switch to my second topic, which is Big Bang nucleosynthesis and how it relates to fundamental constants. You all know that BBN is a cornerstone of the hot Big Bang model, but it has been plagued for a long time by the so-called lithium problem. So there's a significant discrepancy between the theoretically predicted abundance of lithium-7 and what astrophysicists actually observe. Now, from a theoretical point of view, BBN is actually a very interesting physical system to study, because if you choose a fiducial theoretical model, it's actually fairly easy to study BBN in a perturbative way. So from that fiducial model, you can study perturbatively the effects of the various parameters that will change the primordial abundances. So schematically, you can write it this way. So Y are the abundances, X are the relevant parameters, and you have sensitivity coefficients Cij that need to be calculated. Now, this formalism is well known for standard parameters like neutron lifetime, number of neutrinos, variant to photon ratio, and so on. one thing we did recently is to build up on various works in the literature, including work by Victor Flambaum and his colleagues. So we extend this formalism to allow for varying fundamental constants in a full and as far as model dependence allows self-consistent way. So it turns out that there's a broad class of grand unified theory models where you can do this. So you allow all the gauge and Yukawa couplings, all binding energies and so on to vary, and you can express all these variations as a function of the fine structure constant and two model dependent parameters, one coming from quantum thermodynamics, that's the parameter R, and the other one coming from electroweak physics, that's the parameter S. So schematically, the varying couplings part of the perturbative analysis would look like this. Again, Y are the abundances, R and S are model dependent parameters, and X, Y, and Z are sensitivity coefficients that will be different for each of the nuclei, so deuterium, helium 4, etc. So we recently wrote 3 papers on this. The third one has appeared on the archive last week, is in press in ANA. So what I'll do in the next few minutes is highlight the main results of these 3 papers. They include some more analysis that I would have time to explain, but hopefully I can convince you that it's an interesting avenue to pursue. Now, when you try and use BBN to constrain fundamental physics or physics beyond the standard model, this lithium problem is a limiting factor because it's going to be degenerate with some things that you might want to constrain. So in our analysis, we decided to model this phenomenologically, just in a simple way by saying that the astrophysical abundance of lithium-7 that I measure need not be the primordial cosmological one. The two will be related by some depletion factor that we just call delta. So if delta is 0, there's no depletion, and astrophysics observations should mimic or should equal the cosmological ones. But if there's non-zero depletion, then you'll have a difference. And if you do this analysis just with the standard cosmology, but allowing for this depletion, then just essentially by error propagation, you find that you prefer about 70% depletion. But it's also interesting to note that with the latest measurements of cross sections, there is a slight discrepancy in the best fit values of the variant to photon ratio as preferred by BBN and as preferred by CMB, so Planck plus variant acoustic oscillation observation. So this is something that has recently been noted by Pico et al. It relies on a fiducial theoretical model that you assume being the one of Pico et al., so the one that you get from the pre-mat BBN code. And the discrepancy is small, it's less than 2 sigma, but still it's something that we also detect statistically. So here's the posterior likelihood for the baryon photon ratio, so that's the black curve. And the brown vertical bar is the constraint that you expect from CMB plus BBO. Okay, so this is what you do, or what you get in the standard model. Now, what happens in gut models? So if you allow for all these varying couplings, so what you find is that you have a slight preference for a positive value of delta alpha over alpha at the parts per million level. So the preference is at, let's say, 2 to 3 sigma level. And the preferred depletion decreases a little bit, but it's still not 0. So you still prefer about 64 or 65% depletion. Now, in this table, I have results for 3 different models. It doesn't matter that much what they are. You can think of this as just telling you how model dependent the results are. So unification and dilaton are 2 specific gut models. What I call the clock model is not really one specific model. It corresponds to the case where I let R and S vary. So there are additional free parameters. And then I do a joint likelihood with all these parameters, and then I marginalize them in the end. So it's a sort of average result for lots of models in this parameter space. The reason I call it clocks model is that there'll be a degeneracy between R and S and also other parameters. So in order to partially predict this degeneracy, we use some priors from local constraints from atomic clocks. Essentially, these atomic clocks constrain not RNS separately, but some combination of RNS, and this allows some breaking of degeneracies. Okay, so we have a slight reference for a positive value of delta alpha over alpha. Here, in a perhaps more visual form, is how these models work. So what I plotted here, so it's the 4 dBn abundances, so helium-4, deuterium, helium-3, lithium-7. The black points with arrow bars are the theoretically predicted abundances, again, from the pre-mat code of Pico et al. The red points with arrow bars are the observed abundances. So here you see visually the lithium-7 problem. And then, so the purple one is what I get with my best fit model for the standard model plus depletion. So the error bars increase a little bit because you have one more free parameter. And then the green, cyan, and blue is what I get for these 3 models allowing for varying couplings, the unification, dilaton, and clocks. Of course, the best fit model, so the best fit delta alpha over alpha is different for different models. So I'm just plotting the preferred abundances for each best fitting case. And you see several things. So lithium-7 and deuterium are anti-correlated. That's well known, and that's typically a bottleneck if you try to solve the lithium problem, allowing only for varying alpha, but not for the other couplings to vary. Because in order to increase lithium-7 abundance, you're going to decrease lithium, and then you're going to be constrained by observations. Helium-4 and helium-3 are also anti-correlated. But you also notice that different models predict significantly different things. So these models are potentially testable. So for example, the dilaton model over-predicts helium-4 as compared to the other 2 models. So here I forgot to mention that in the case of lithium-7, I plot both the cosmological abundance on the top part and the astrophysical abundance, so corrected by this depletion factor. Now, the interesting thing is what drives this preference for a non-zero delta alpha over alpha. You might think it's lithium-7, but it's not. So in the previous slide, I had the results for what I call the baseline data set, which includes lithium-7. If I remove lithium-7 from the analysis, so this is what I call the null case, I still have a preference for a non-zero delta alpha over alpha. So what is driving this value is actually this slight discrepancy between the observed and measured deuterium abundances, or if you prefer, the slight discrepancy in the baryon to photon ratios as measured by the CMB and BBN. And you can see that here. So here's the 2D plane of delta alpha over alpha versus the baryon to photon ratio. And these are 1, 2, and 3 sigma constraints for the 3 models. So there's a positive correlation between the 2. It's not so easy to see in the clocks model because the parameter space is more awkward. But if you want to get the baryon to photon ratios of CMB and BBN to agree, you have to increase the value of alpha slightly. So it's deuterium that is driving this small preference for positive delta alpha over alpha. This goes in the right direction for solving the lithium-7 problem, but it's not enough. So you still need an astrophysical mechanism. And in our latest paper, we describe in detail how lithium-7 can be depleted in stars, and we think that lithium-7 can be, so the problem is mainly solved by this depletion.
Carlos, you have 10 minutes to go, about 10 minutes.
Right, thank you. Now you might ask, does helium-4 matter? The answer is not too much with current data. So these constraints are really driven by deuterium. So you can see this here. You have constraints on delta alpha over alpha, marginalizing over everything else for deuterium only, or deuterium plus helium-4, with other cosmological parameters fixed or marginalized. And you can see that for the unification and clocks models, there's basically no change. The error bars increase if you let other cosmological parameters vary. But the preferred value of alpha is not changed. For the dilaton model, there is a significant change if we include helium-4 for the reason that I mentioned earlier. In this model, you over-predict the abundance of helium-4. So therefore, if you include the helium-4 in the analysis, you're going to be penalized and the preferred value of alpha decreases. Okay, so I think I'm on time, so let me move on to my last point, which is the impact of measurements of alpha in cosmology and particle physics. So you can think of two different classes of models, what we call class 1 and class 2. So in class 1, the same degree of freedom gives you both dynamical dark energy and the varying alpha. And in this case, the evolution of alpha is essentially parametrically determined, in the sense that if you know how dark energy evolves, you know how alpha evolves with redshift. So therefore, you can use alpha measurements to constrain dark energy and vice versa. And alpha measurements in particular allow you to distinguish between different classes of models, including what's called freezing and thawing dark energy models. So one example of this class would be quintessence type models. In the second class, the dynamical degree of freedom that gives you the alpha variation that does not give you the dark energy, or at least does not give you all of it. In this case, if you assume it's the same degree of freedom giving you both, you're going to make a mistake, of course, but this is something that you can check. There are consistency tests that you can make. These classes are interesting because in some cases, varying alpha might be the only way to distinguish these from lambda CDM, because otherwise the constraints put you so close to lambda CDM that you will not see differences with cosmological data. So examples of these are Bekenstein type models and Dirac-Born-Infeld type models. It's also important to note that these measurements constrain the weak equivalence principle. This models scalar field couples to nucleons, so the weak equivalence principle is violated. And actually, if you combine alpha measurements, so the current data, with the Utrecht parameter constraint by microscope, you improve the microscope constraint by a factor of 3. So microscope has new results coming out, which will improve their bounds. But we also have Espresso results coming out, which will improve our measurements. So we're quite looking forward to combine the new results on both sides, because we can significantly improve constraints. So finally, let me just make one further digression, and so talking about the synergy between alpha measurements and cosmology measurements. So in the Euclid Consortium, we recently wrote a paper describing how we can combine alpha measurements with Euclid data and use the combination to constrain dark energy models. And essentially the result is that adding alpha data improves the dark energy figure of merit that Euclid would get by between 8 and 26%, depending on whether or not you have an alpha variation, so whether the fiducial model is lambda CDM or not. And essentially the gain here comes from the big redshift lever arm. With alpha measurements, you have data all the way up to redshift 4. And again, if you want to constrain something that might be moving slowly, the bigger redshift lever arm you have, the better. Okay, so that's what I wanted to say. So again, just to summarize, the acceleration of the universe shows that our canonical theories are incomplete. You should search for these new physics, and precision astrophysical spectroscopy is a very useful tool in this quest. At the moment, we know that there's nothing varying at the level of few parts per million. That's already a very strong bound. It's stronger than the Cassini bound in a solar system, and it provides the best available weak equivalence principle constraint. There's new results coming out, so the microscope constraints, Espresso data, and so on. So the prospects are good. And in the next generation, we'll have the ELT, which will provide even more stringent tests, including tests of composition-dependent forces, direct measurements of the expansion of the universe through the redshift drift, and so on. So I think the field is in good shape, and future looks bright. So that's all I wanted to say. So thanks for your attention, and I'm happy to take questions.
Thank you very much, Carlos, for the nice talk. Are there any questions? Also, we had another related talk yesterday, actually, by Sebastian in our session, where he discussed the possibility of the H0 discrepancy between high redshift measurements and low redshift measurements, and the possibility in terms of having variant alpha, and also this sort of modified H0 as a possible explanation to the lithium discrepancy, lithium puzzle. What is your opinion on the relation of the H0 tension to the lithium problem?
Well, so I have to say I missed yesterday's talk. I was chairing my own session on topological defects, so I'll try to catch up with that talk when the video appears. So for the alpha constraints we get at the parts per million level, there's no real impact on cosmology, right? It's too small to have any effect. Now, if you add variations of alpha that were larger at, let's say, 10 to minus 3 level, which is the current constraint from CMB, there, I guess you have a partial effect. So there's these papers by Luke Hart and Jens Kluber, I believe, who discuss this a little bit. So yeah, I think to have an impact on the H0 tension, you need to be at 10 to minus 3 level or above. So in our case,
that's right. It was, I think, 10 to minus 3, 10 to minus 2 in that sort of range.
Right. So I guess we're talking about different models. So in our case, the constraint is 10 to minus 6, right? In these gut type models. So the 10 to minus 3 is completely ruled out by BBN data. So the other side of this coin, if you want, is that with a 10 to the minus 6 variation of alpha, we can also not solve the lithium problem. It goes in the right direction, but it only decreases your depletion from 70% to about 64, 65%. But honestly, I tend to believe, so this recent paper I wrote with Morgan Deal, who was a specialist on chemical evolution in stars. And the impression I have from discussing with him is that a 60 or 70% depletion is not difficult to get in stars. So stellar evolution can do that for you. So that's a more standard explanation, maybe slightly less exciting, but it seems to be possible.
Thank you very much. We do actually have a question from Sebastian, who was yesterday's speaker on this on the related topic. Sebastian, please.
Yeah, thanks. I would like to ask you about one of your last plots, Carlos, because I was happy to see in one of your first slides that you have a delta alpha that was negative, and then I think in the penultimate slide you show that it should be positive. Is that right? Did I get it right?
No, for BBN, the preferred value of delta alpha over alpha is always positive in all models.
Well, I mean, you have shown the quasi-spectra analysis.
So there, well, let me maybe share the slides again so we can be sure that we're talking about the same slide. Oops. So tell me when to stop. Is it this one or
this one? Yeah. Just do one more. There. Yeah.
This one.
So at that point, the trend is like it should be negative for large redshifts.
No, I mean this is consistent with 0 at 1 sigma, so there's no detection.
Okay, but then in the penultimate slide, you have a plot on the bottom part and left part of the screen. That one, yeah. I mean, what is that?
So this comes from our Euclid paper. So the most recent one, the 2011. So what Euclid wants to do is constrain dark energy, right? So these are the usual W0 and WA parameters for dark energy equation of state, and this zeta is the coupling of the scalar field to the electromagnetic sector. So it's not alpha.
Okay, sorry. I just
and in this case, the fiducial model is lambda CDM. So yeah, you recover 0. We also do an analysis in the paper with a fiducial model where alpha does vary. So I didn't include the plot. But yeah, so essentially what happens for the purposes of the cosmological analysis is that you have your dark energy parameters, W0, WA, omega matter, and so on. And what you constrain additionally is the coupling of the scalar field to the electromagnetic sector.
okay. Thanks.
So we have time for one final quick question. So I don't see any questions, any further questions. So I'd like to thank Carlos again. And
thank you.
Our next speaker is Stefan Ulmer from Riken, based at CERN. Stefan, if you'd like to share your slides, please.
Yes, just 1 second. Good morning, everyone, or hello, everyone. Okay, so slides are shared. Can you see this?
Yes, I can see your slides. Would you like to try full screen?
Full screen. Okay, should be on. Is
Perfect.
audio quality okay and everything good here?
Audio quality is good, but you're a little bit quiet.
Okay, I just try to speak up. Okay, perfect.
Whenever you're ready, please. Thank you.
Okay, thanks very much for the invitation, Evgeny, and to the other organizers. I will talk about studies of exotic physics with antiprotons and protons in penning traps. I'm representing here the BASE collaboration of CERN. In fact, BASE is a slightly larger project. We are operating at the moment 3 experiments. One at the University of Mainz, one at the AD of CERN, which is in fact our main experiment and a kind of future perspective experiment at the University of Hanover, where we are working on the implementation of sympathetic cooling of single trapped antiprotons and quantum logic inspired readout of the spin eigenstate of the particle. Before I start with the talk, I want to show you something. So if you can hear this, what you're listening to at the moment is the sound of a single antiproton in a penning trap, and so mixed to audio frequencies. The concept how this principle works is that the particle is oscillating in the trap, and this oscillation induces image currents into the trap electrodes, oscillating at the frequency, at the same frequency as the particle in the trap. And these image currents, which are of the order of femtoamps, can be amplified by means of highly sensitive superconducting image current detection systems. Then the resulting voltage signals are being amplified and finally FFT analyzed. And this is how we are measuring frequencies of single particles. If you listened very carefully, you even became aware that the pitch of the particle, I mean the frequency, slightly changed. This is due to resistive cooling. The particle interacts with the detection resistor. This takes energy out of the particle, and due to special relativity changes the oscillation frequency. So what you've just heard is the sound of something which does not naturally exist to high abundances in the universe, the sound of a single trapped antiprotons, frequency modulated by special relativity. And in BASE, we are kind of listening to the sound of these extremely simple systems to kind of test CPT invariants, detect exotic physics, which would appear as changes in pitch and frequency beating and so on and so forth. Of course, the motivation to these experiments is matter-antimatter symmetry. If we combine the lambda CDM model and the standard model, our prediction of the baryon to photon ratio is inconsistent by about 9 orders of magnitude. So the naive expectation would be a baryon to photon ratio at the level of 10 to the minus 18. So purely radiative universe and matter-antimatter balance. What we are actually observing is a baryon to photon ratio at the level of 6 times 10 to the minus 10 and a strong matter-antimatter imbalance, which can be explained, for example, I mean, in models by Sakharov, which requires B violation, CP violation, which has been observed but is too small to explain this number here. And the Sakharov conditions also require an error of time. Alternative source would be CPT violation, which kind of adjusts matter-antimatter symmetry by a natural inversion given the effective chemical potential then of the early universe. So experimental signatures which are sensitive to CPT violation can be derived from precise comparisons of the fundamental properties of simple matter-antimatter conjugate systems, and this is what we are in fact doing at the antiproton decelerator of CERN. And also say a few words about the fundamentality of CPT invariance. So a relativistic quantum field theory which conserves CPT requires only basically 5 basic ingredients, which is Lorentz and translation invariance, energy positivity, microcausality, the existence of a stable vacuum ground state without momentum nor angular momentum, and the possibility for a unitary field operator's interpretation. So if these 5 basic ingredients are given, the resulting theory is CPT invariant. There's still a motivation to search for CPT violation. I mean, obviously the cosmological matter-antimatter symmetry, but also more fundamental string theories, loop quantum gravity, non-commutative field theories, brane scenarios, they all induce basically CPT violation. So the question is which type of measurable signatures of these BSM theories would be imprinted onto the structure of the vacuum box of relativistic quantum field theories, or in different words, what is the standard model Lagrange density and how would CPT violation in principle be imprinted onto this Lagrange density. And in order to try to find replies to these questions, Kosteletsky and co-workers constructed an effective field theory in an axiomatic way, the so-called standard model extension, which contains the standard model and general relativity, but adds CPT violation, and the resulting modifications of the standard model Lagrange density look like this. They consist of an expectation value of some physics which has been projected, I mean, some maybe higher dimensional physics, which has been projected to Minkowski space, suppressed by a mass scale. There's an effective coupling strength, and then these Lorentz bilinears. And we are, for example, in magnetic moment comparisons sensitive to DC shifts of the first order in K of this effective modification, which would correspond to a pseudomagnetic field mediated by the respective field here. Different tests of CPT invariance have been carried out so far. Just to set this work in context, for example, very prominent, the K0 bar mass comparison at a fractional precision at a level of 10 to the minus 18. Electron-positron magnetic moments have been compared with a fractional precision at the level of 10 to the minus 12 by Demelt and collaborators. very prominent recently, of course, also the muon G-2 comparisons. And at the antiproton decelerator of CERN, we are comparing the fundamental properties of hydrogen and anti-hydrogen. This is being done by the alpha collaboration. Meanwhile, measurements at the level of parts per trillion are available. In base, we are comparing charge to mass ratios and magnetic moments. And for example, the alpha collaboration is operating a project on antiprotonic helium spectroscopy. They get access to the antiproton to electron mass ratio. The main tool which we are using for these type of measurements is the penning trap, and the strength of the penning trap is that it's a beautifully simple device. It's basically just a magnetic field, a very homogeneous magnetic field, which is stable. So charged particles are constrained to cyclotron orbits, and in order to prevent the particles from escaping along the magnetic field lines, we superimpose on this magnetic field an axial electrostatic quadrupole potential. In such a combination of crossed electric and magnetic static fields, a single particle, the trajectory of a single particle develops to become a combination of three independent harmonic oscillators. The axial oscillator along the magnetic field lines, the magnetron oscillator, and the modified cyclotron oscillator, which is basically the free cyclotron frequency slightly modified by the radially pulling potential. What makes penning traps two particularly interesting tools for precision measurement is that such an invariance theorem is valid. So if we measure the three trap oscillation frequencies and evaluate the root of the square sum, we end up at the free cyclotron frequency. And this relation is very robust with respect to typical first order trap imperfections, such as, for example, a misalignment between the magnetic axis of the trap and the electrostatic axis of the trap. So there are basically two different types of precision measurements which can be carried out in penning traps. So first of all, measurements of cyclotron frequencies. And if we measure cyclotron frequencies of different particles, we get access to ratios of charge to mass ratios. This is known as high precision mass spectrometry. In addition to measurements of cyclotron frequencies, I mean, based on image current detection, we can also measure Larmor frequencies, so the spin precession frequency. So if we measure these two frequencies and evaluate the ratio of those, we get access to G factors, or in different words, magnetic moments, in our case, the magnetic moment of the antiproton in units of the nuclear magnetron. So the takeaway information here is that the determination of charge to mass ratios and G factors in penning traps reduced to simple frequency ratio measurements. So conceptually, these experiments are very simple, which gives us, on the other hand, full control. We are just directly measuring the quantities we are interested in. Almost no theoretical corrections are required. Just to give you an idea how such a penning trap experiment looks like, I mean, this here is the base experiment at CERN. The length here is about, well, 3 meters. These are cryostats. I mean, all the penning trap experiments are operated under cryogenic conditions, at least the high precision ones. And then we have here in the center a superconducting magnet. This here is our radio frequency control rack. And inside the superconducting magnet, the trap system is located. We are currently operating a 4-trap system with a reservoir trap for antiprotons, which enables us to decouple from the accelerator once the reservoir is full. A precision trap, which is a very homogeneous trap. In this trap, we perform the high precision frequency measurements. Then we have a cooling trap and an analysis trap. I will talk about these two later. So let me start talking about the antiproton to proton charge to mass ratio measurements. So in base, one frequency ratio measurement takes about 240 seconds. This is about 50 times faster than in this pioneering experiment, which has been conducted by Jerry Gabriels and his group in 1999. So we have very high sampling rates, and this is achieved by using a multi-trap stack. This is a multi-trap stack. Here you can see the measurement trap, this reservoir trap. We load the reservoir, then we pinch a single antiproton out of the reservoir trap, and afterwards a single H- ion, and park the particles in this potential configuration. So we start with an H- ion in the measurement trap, measure the cyclotron frequency. This is based on image current detection. Then we shuttle this configuration here to that configuration, park the second particle in a park trap, and measure the cyclotron frequency of the antiproton. And one of these measurements, as said, takes 240 seconds, which is fast. Also, one additional remark: we are not comparing protons and antiprotons. We are comparing antiprotons and negatively charged hydrogen ions, because the negatively charged hydrogen ion, as you can see here, is a perfect proxy for the proton, but with a negative charge. And this avoids, or in consequence, the inversion of the trapping potential can be avoided, which suppresses certain systematic shifts, frequency shifts, by up to a factor of 300 compared to a proton-antiproton comparison. So given this method, we've acquired in 2015 already 6,500 proton-antiproton charge to mass ratio comparisons. And with this experiment, we've reached fractional precision with of about 69 parts in a trillion. This is one of the most stringent tests of CPT invariance with baryons, and it's consistent with CPT invariance. We also have a new measurement online where we acquired 35,000 frequency ratio measurements distributed over 1.5 years. So this is a really massive data set still under analysis. We used here 2 different measurement methods in an entirely rebuilt apparatus, which is intrinsically much more stable than the old apparatus. This you can see here. So this red histogram is the frequency stability, which corresponds to this measurement, and this blue histogram is what we achieve at the moment. So we have these 2 measurement campaigns, and it looks like that we will be improving this value after finalization of this data evaluation by about a factor of 5. In addition, we will have the possibility for very different oscillation studies on this data set. I'd like to mention one kind of physics interpretation of these results, which is a test of the weak equivalence principle based on clocks. So assume that CPT is invariant and no gravitational potential is present. Then the cyclotron frequencies of protons and antiprotons would be identical by definition. If there is now any violation of the weak equivalence principle for antimatter, or any gravitational anomaly, for example, coupling to antiprotons, and if we switch the gravitational potential back on again, for example, by bringing the particles to the surface of the Earth, the antiproton would experience a different gravitational redshift than the proton. And given our result, we can constrain, in principle, this anomaly parameter down to a level of 10⁻⁷. This interpretation has been discussed controversially because it's sensitive to absolute values of potential. So what we would want to do as well is basically to set differential constraints on the weak equivalence principle just by measuring the charge to mass ratio as a function of the gravitational potential while the Earth is circulating on its trajectory around the sun. This is under evaluation. We are also able to set constraints on standard model extension coefficients. So all these constraints are improved by our recent measurement by about a factor of 4. Okay, in base we are reaching now slowly the limits which are imposed by the accelerator hall. So we have an accelerator running in the background while we are performing precision frequency measurements. We have a few more years to go in this facility here at CERN, but on the long term we need to move the particles out to dedicated CARN laboratory space. And this is what we are planning to do. So my colleague Christian Smora got an ERC grant for this. And within this project, he's developing the instrument base STEP, which is a transportable antiproton trap. And at the moment, we are discussing with CERN for offline laboratory space, so outside of the accelerator hall, to further improve our high precision antiproton frequency measurements.
Oh, Stefan, you have 10 minutes to go.
10 minutes to go. Thanks very much, Evgeny. That's quite sufficient, I hope. So let me now move to another experiment. I mean, the measurement of the antiproton magnetic moment. This is the much more difficult experiment compared to the charge to mass ratio experiment, because we need to measure the Larmor frequency, not only the cyclotron frequency. Cyclotron frequency measurements are straightforward. They rely on image current detection. The measurement of the Larmor frequency is in that sense difficult, that the spin precession is not accompanied by a shift of charge. So we cannot pick up the Larmor motion by any type of image current, so we need to apply a trick, and this trick has been invented by Hans Dehmelt. He called it the continuous Stern-Gerlach effect. And to explain here the details, consider a magnetic moment in a magnetic field and the related magnetostatic energy. So if we superimpose on our trap an inhomogeneous magnetic field, the interaction of the magnetic moment with this inhomogeneity adds a spin-dependent quadratic potential to the axial electrostatic quadrupole potential, which means that the axial oscillation frequency becomes a function of the spin eigenstate. So to measure the Larmor frequency, we just need to measure basically the axial frequency. Induce a spin transition, measure the axial frequency again. If we repeat this for several hundred times and different drive frequencies, we get access to the spin flip probability as a function of the drive frequency, which is applied to flip the spins. And this gives us such a Larmor resonance with a very sharp cutoff, and this cutoff is the zero energy Larmor frequency, exactly the quantity we are interested in to determine the magnetic moment. Conceptually, this is a simple experiment. Here the challenge is in the details. The axial frequency shift, which is induced by a spin transition, is proportional to the magnitude of the magnetic moment, to the strength of the magnetic inhomogeneity, and anti-proportional to the mass. So this concept has been applied very successfully to electrons. If we compare here this figure of merit magnetic moment over mass for protons, antiprotons, and electron positrons, we become aware that the sensitivity here is, in case of the antiproton, more than 1 million times smaller than in case of the electron positron system. So we superimpose on our trap a very strong magnetic field inhomogeneity, about 300,000 Tesla per square meter. That's a massive gradient. And under these extreme conditions, our spin flip detection signal is a frequency shift of about 170 millihertz out of roughly 1 megahertz. One difficulty is basically imposed by the magnetic bottle. This magnetic bottle is so strong that single particle, single trap measurements in magnetic bottles limit basically the resolution of the experiment to the parts per million level. In order to overcome this difficulty, we have invented a new technique, a two-particle, three-trap method. In this method, we divide basically the spin state analysis and the high precision frequency measurements to two particles and two traps. So the method works as follows. We have here a very cold spin state analysis particle in this analysis trap. So this is the trap with the strong superimposed magnetic bottle. This here is a very homogeneous trap. So we analyze the spin state of this particle, then we use the second particle and measure the magnetic field in this precision trap by image current detection. Afterwards, we shuttle the particle assembly such that this particle ends up in this part trap and the second particle in the center of the precision trap. Then we flip the spin of this particle, shuttle the configuration back, measure the cyclotron frequency again, and analyze the spin state of this particle later on. What this method does is that it basically measures the magnetic moment, applying basically this principle here, or measures the Larmor frequency, however, in the homogeneous magnetic field of this precision trap. And here is an example for a single particle, single trap Larmor resonance, and so measured in this trap here. And when applying this two-particle three-trap method, we end up here at this Larmor resonance. So these are measured data, and if we zoom in here, we obtain this very nice Larmor resonance curve, which enables us to determine the G factor of the antiproton with a fractional precision of about 1.2 parts in a billion. At the time when this was achieved and published, the proton magnetic moment was even known with lower resolution. So this was for the first time that an antimatter fundamental constant was more precise than the corresponding constant of the matter counterparts. However, I mean, both of these experiments are operated by the Base collaboration. So at the Base Minds experiment, we later on improved the value of the antiproton magnetic moment compared to this one by a factor of 11. So now the antiproton is less precise than the proton again, but the combination of both methods improves the previous best magnetic moment based CPT tests by a factor of 3,000 compared to earlier work. We were also constraining, I mean, with the help of Yevgeny, our data set and performed the time-based analysis and looked basically into antiproton axion anomalous coupling. So this is the effective Lagrange density, and in a very simplistic translation, this interaction of this interaction, basically the axion dissociates to photons which interact then with standard model particles. We are looking here for cold dark matter, which is gravitationally bound, and this cold dark matter is expected to oscillate through the galaxy at an effective Compton frequency, which is proportional or basically defined by the mass of the dark matter. And again, this dark matter imposes in principle an interaction which would look like a pseudo magnetic field, and this would effectively lead basically to broadening and sidebands in our Larmor resonance. And investigating the time series of our data for such broadening effects, we were able to set stringent constraints on antiproton dark matter interaction. Before I come to an end, do I have one more minute, Yevgeny?
Well, you still have a few more minutes, yes.
Yeah, okay, perfect. So I'd like to talk about a last project which we were just working on. This is a project which is for the first time now not related to antimatter anymore. So it's much more related to single particle detectors in panning traps. So these single particle detectors, they are extremely sensitive devices, and we just made the question whether we could do something else with them, something else rather than detecting basically oscillation frequencies of single particles. And it turns out that we can use them to constrain the coupling or to set limits on the conversion of axions to photons. So as already said, axions at the right quantum frequency would source a radio frequency signal that could be picked up by these single particle detection systems. At the right quantum frequency means that if the mass of the axions is just such that they are at resonance with our detector. So in the very strong external magnetic field of our superconducting magnet of the panning trap experiments, axions will convert into photons via the inverse Primakov effect. And if we do the math here, we realize that the axions would source basically a circular magnetic field in our detection systems, which can be picked up by our toroidal resonator. So what we would expect if there would be an axion signal is that we would see on our noise resonance of the detector some peaks which have yet to be understood, and we would be able to tune these peaks away, for example, by varying the external magnetic field of our instrument. Okay, this here is the effective voltage drop which is induced by the axion signal in such a resonator, and the noise floor. The noise floor is proportional to the temperature of the detector, and we are using the single antiproton to determine this temperature. So this is a model-independent noise measurement, basically, of the or noise characterization of the noise power on this resonator, which enables us to set very clean limits here, because we are using the single antiproton as a single particle thermometer. And on this landscape here, we were setting this very narrow band limit. It's extremely narrow band, but already competitive or at the same order of magnitude as astrophysical experiments. And since we have this technology at hand and the sensitivity of such experiments scale basically proportional to the volume of the detection resonator, temperature, detection Q, everything can be increased if we basically build a device which is not a panning trap, which requires a lot of space, but which fills the magnet up with resonators. And this is what we are developing at the moment. We will operate this experiment at smaller temperature. We have built already detectors with fourfold improved quality factors, are developing amplifiers with lower noise, will operate this experiment at higher magnetic field, can increase the geometry, the effective detection volume by a factor of 16. So in a first generation experiment, this would enable us to improve this limit, which we've set in this example evaluation, by a factor of 260. We were also developing a bandwidth tuner, which increases basically the width of this detector by more than a factor of 3,000. So we are hoping to bring this experiment to operation within the next year. So, and with that, I'd like to summarize. I've reported on the status of an improved proton-antiproton charge to mass ratio comparison, reported on the improved measurement of the magnetic moment of the proton with an improved precision of a factor of 11, for the antiproton, a factor of 3,000. We were using antimatter as antennas for dark matter detection. I've also summarized the status of using single particle detectors as antennas for axions, and quickly flashed the development of our transportable trap, which will enable us to measure at higher precision in the future. And with that, I'd like to thank you very much for your attention.
Thank you very much, Stefan, for the nice talk. Are there any questions? We have time for a couple of questions. I actually had a question, Stefan. So in your axion to photon conversion search, what is the strength of the magnetic curvature that you use in this experiment?
You mean the magnetic field strength?
Well, magnetic field strength, and also is there a sizable magnetic curvature as well, like a bottle field on top of this?
Would this be in any sense helpful, Evgeny?
Probably not, but I'm just curious. Do you basically just apply as homogeneous magnetic field as you can possibly do? Like, for example, in your, what's the name of it? The precision traps, the analog rather than analysis trap.
Yes, yes. So I mean, in this axion search, the magnetic field is varying over the resonator, I think, with a peak-to-peak variation at the level of maybe 5 × 10⁻⁵. So there is no curvature at all, I would say. So it's a very homogeneous magnetic field, and the absolute magnetic field strength, and this is basically defined by the requirements of the Penning trap experiment, is in case of this study here at 1.945 Tesla. But for this purpose-built experiment, I mean, we are planning to use a superconducting magnet, which is being operated at 7 Tesla, and these 7 Tesla will be homogeneous also at this level, let's say peak to peak 10⁻⁴ over the entire central detection resonator.
Thank you very much for explaining. Are there any other questions? We have time for, I think, one question before we have to close the session. Well, I don't see any questions or hands raised. So in that case, I would like to thank Stefan and all of the speakers in our session today for the excellent talks. So I've noticed some speakers have already uploaded their slides to the Indico website. Thank you very much. We'd like, of course, for all the speakers, if possible, to upload their slides. And also, we will also have another session on Thursday. This will be the final session, and that'll be at 16:30, so that's 4:30 p.m. Central European Standard Time. So we hope to see you all again on Thursday, and thank you all very much for the excellent talks. So I think we have, in principle, time for any outstanding questions, I guess, to the other speakers before we get cut off automatically at some stage. If there's any outstanding topics which weren't covered. Okay, I don't see any raised hands. So in that case, I propose that we close the session, and I look forward to seeing you all on Thursday. So that's Thursday afternoon session. Bye-bye.
Bye-bye. Thanks very much.